In the summer of 1942, Winston Churchill received a proposal that seemed to belong in science fiction rather than strategic planning. The memorandum, presented by a brilliant but eccentric inventor named Geoffrey Pyke, suggested that Britain could solve its acute shortage of aircraft carriers by building them from ice, not steel-plated with ice for protection, not wooden ships operating in frozen waters. Actual aircraft carriers constructed from frozen water, 2 million tons displacement, 2,000 feet long. Their hulls composed of a material that was bulletproof, torpedo-resistant, unsinkable, and could be manufactured in vast quantities using resources that Germany could not interdict. The proposal seemed absurd on its face, the kind of crackpot scheme that serious military planners would dismiss without consideration. Churchill read it twice, consulted his scientific advisors, and gave the project his personal approval. For the next 18 months, British and American engineers would pursue one of the most ambitious and bizarre projects of the Second World War, attempting to transform frozen lakes into floating airfields that would dominate the Atlantic and end the U-boat threat forever. The project was codenamed Habbakuk, after a biblical prophet, and it came closer to reality than most historians realize. The strategic context that made ice carriers seem reasonable, rather than insane, was Britain's desperate position in the mid-Atlantic. German U-boats were sinking merchant ships faster than replacements could be built, targeting convoys in the gap between the range of land-based aircraft operating from Britain and from Newfoundland. This gap, roughly 600 miles wide, was where convoys were most vulnerable, where submarines could operate without fear of air attack, where losses mounted to unsustainable levels. Aircraft carriers could close this gap, providing air cover throughout the Atlantic crossing, but Britain had too few carriers and needed them for other operations. Building conventional carriers required steel, shipyard capacity, and time that Britain did not have. Germany's submarine construction was accelerating. Convoy losses were accelerating faster. Something had to change, and conventional solutions were proving inadequate. Geoffrey Pyke was not a conventional thinker, which was simultaneously his greatest strength and his greatest liability. He was a journalist, inventor, and self-taught scientist who had spent the interwar years pursuing schemes that ranged from brilliant to delusional. He had been arrested as a spy during World War I, escaped from internment in Germany, and written a book about the experience. He had started a school based on progressive education theories. He had developed camouflage techniques, snow vehicles, and a dozen other projects that military authorities sometimes adopted and often rejected. His mind worked in ways that generated both insights and absurdities, often intermingled so thoroughly that distinguishing between them required careful analysis. The ice carrier was quintessential Pyke, audacious, unconventional, based on sound physics, but requiring engineering that pushed every boundary. The physics behind Pyke's proposal was straightforward. Ice floats because it is less dense than water. Ice is strong under compression, capable of bearing enormous loads if properly supported. Ice can be shaped and molded when partially melted, then refrozen into desired configurations. Most importantly, ice is effectively immune to torpedoes and bombs. A torpedo exploding against an ice hull would create a crater, but would not sink the vessel because ice, unlike steel, does not transmit shock waves that rupture adjacent compartments. A bomb penetrating an ice deck would melt a hole, but would not cause catastrophic structural failure. An ice ship damaged in combat could be repaired simply by freezing more water into the damaged areas. The material properties that made ice useless for conventional construction made it potentially ideal for a vessel that needed to survive combat damage rather than avoid it entirely. The practical challenges, however, were daunting. Pure ice, while strong under compression, is brittle and fractures easily under tension or impact. It melts at temperatures above freezing, requiring either continuous refrigeration or operations in Arctic waters. Its surface is slippery, making it unsuitable for aircraft operations without modification. Its optical properties make it transparent or translucent, creating visibility issues for internal compartments. Pyke addressed each of these problems with characteristic ingenuity, but each solution created new engineering challenges that required resolution. The breakthrough that transformed ice from interesting concept to plausible construction material came from one of Pyke's collaborators, a researcher named Herman Mark, who had been experimenting with reinforced ice. Mark discovered that mixing wood pulp with water before freezing produced a composite material with vastly superior properties to pure ice. The resulting substance, which they named Pykrete after its inventor, was only 14% wood pulp by weight, but exhibited strength and toughness that pure ice could not match. Pykrete could withstand bullet impacts that would shatter pure ice. It melted much more slowly, its wood fiber content providing insulation. It could be sawed, shaped, and machined like wood while retaining ice's basic structural properties. Most remarkably, it was effectively unsinkable. If damaged, the material simply floated as ice chunks. An additional Pykrete could be frozen onto the damaged areas for repair. The demonstration that convinced Churchill and the British War Cabinet of Pykrete's potential took place in Quebec in 1943 during a conference attended by Churchill, Roosevelt, and combined chiefs of staff. Lord Louis Mountbatten, who had become Habbakuk's most enthusiastic military advocate, arranged a demonstration using blocks of pure ice and Pykrete kept frozen in a bathtub. He fired his pistol at the pure ice block, which shattered dramatically. He then fired at the Pykrete block, which resisted the bullet and caused it to ricochet around the room, narrowly missing several high-ranking officers. The demonstration was theatrical and dangerous in equal measure, but it achieved its purpose. The attendees could see with their own eyes that Pykrete was not normal ice, that it possessed properties that might justify the audacious construction project Pyke had proposed. The design that emerged from 18 months of engineering work was staggering in scale and ambition. The Habbakuk carrier would be 2,000 feet long and 300 feet wide, displacing over 2 million tons, roughly 20 times the displacement of a conventional aircraft carrier. Its hull would be constructed from Pykrete 40 feet thick, providing protection that no torpedo or bomb could penetrate. Inside this hull would be a network of refrigeration equipment, maintaining the structure at temperatures below freezing even in temperate waters. The flight deck would be wood planking over steel framework, itself supported by the Pykrete hull. Propulsion would be provided by electric motors powered by diesel generators, producing enough thrust to move the massive structure at a stately 7 knots. Aircraft hangars, workshops, crew quarters, and storage spaces would occupy the interior, creating a floating city capable of supporting 100 aircraft and a crew of thousands. The construction plan called for building Habbakuk in frozen Canadian lakes during winter months. Large frameworks would be erected, pumps would spray water and wood pulp mixture over the frameworks in layers, and natural freezing would produce the Pykrete hull over a period of months. Refrigeration equipment would be installed as construction proceeded, eventually maintaining the structure independently of external temperatures. The completed carrier would be towed to the Atlantic through the St. Lawrence Seaway, where it would begin operations covering the mid-Atlantic gap that conventional carriers could not adequately patrol. The prototype built to test these construction methods was a scale model constructed at Patricia Lake in Jasper National Park, Alberta. This prototype, called the Habbakuk test ship, was 60 feet long and shaped like a simplified ship hull. It contained refrigeration equipment scavenged from commercial sources, insulated with sawdust, and powered by a diesel generator running continuously. The structure was built during the winter of 1943, using the spray freezing technique that would be scaled up for full construction. It successfully demonstrated that Pykrete could be fabricated in large structures, that refrigeration could maintain the material in summer conditions, and that the basic engineering concepts were sound. The test ship also revealed the magnitude of the challenges that full-scale construction would face. The refrigeration requirements were enormous, consuming power that would require massive generating capacity. The insulation needed to reduce heat transfer was itself a major engineering challenge. The structural framework required to support the hull during construction had to be strong enough for the loads, but also needed to remain embedded in the final structure. Most critically, the time required for construction was measured in months, even for the small prototype. A full-scale Habbakuk would require years to build using the spray freezing technique, by which time the war might be over or the strategic situation transformed. The cost analysis conducted by British and Canadian engineers provided sobering realities that enthusiasm could not overcome. A single Habbakuk carrier would require approximately 280,000 tons of wood pulp, an amount that represented a significant fraction of Canadian paper industry output. The steel required for internal structure, propulsion, and equipment would exceed the tonnage needed for multiple conventional carriers. The electrical generating capacity needed for refrigeration would consume resources that could otherwise produce submarines or escort vessels. The construction time, even under optimistic assumptions, would be longer than the time required to build conventional carriers in American shipyards that were finally reaching full production capacity by mid-1943. The changing strategic situation gradually eroded Habbakuk's rationale, even as engineering work continued. The Battle of the Atlantic began turning in the Allies' favor during 1943, partly due to improved radar, partly due to increased escort numbers, partly due to long-range aircraft that began closing the mid-Atlantic gap that Habbakuk had been designed to cover. American shipyards were producing escort carriers, small, cheap aircraft carriers converted from merchant hulls at rates that made ice carriers seem redundant. The Casablanca-class escort carriers could be built in months rather than years, cost a fraction of what Habbakuk would require, and provided capabilities that met 90% of operational needs even if they lacked the invulnerability that Pykrete promised. The project was quietly cancelled in late 1943, officially due to resource constraints and competing priorities, unofficially because it had become unnecessary. The prototype at Patricia Lake was abandoned, its refrigeration equipment removed, its structure left to melt naturally over the following months. Plans and documents were classified. The work that had been done was dispersed across multiple agencies, and Habbakuk faded from wartime attention with remarkable speed. The project had consumed significant resources and engineering talent without producing operational results, but it had not been a waste in the sense that military failures are typically measured. Habbakuk had been insurance against scenarios that fortunately did not materialize, investigation of concepts that might have been essential if conventional solutions had failed. Geoffrey Pyke did not handle the cancellation well. He had invested enormous emotional energy in the project, believing that his ice carriers would be recognized as a decisive contribution to victory. The cancellation confirmed his long-standing belief that military establishments rejected innovative thinking, that bureaucratic caution prevented the bold moves that war demanded. He continued proposing schemes and inventions throughout the remainder of the war and after, but Habbakuk represented his last chance at major influence. He committed suicide in 1948, despondent over financial difficulties and the rejection of his ideas, never knowing that Habakkuk had come far closer to realization than most abandoned projects ever do. The prototype structure at Patricia Lake remained partially visible for decades after the war, its framework and residual Pykrete resisting decomposition longer than anyone expected. Eventually, the site was cleaned up and the remaining materials removed, leaving only foundations on the lake bottom. These foundations were rediscovered in the 1970s when the story of Habakkuk was declassified and began attracting historical interest. Today, the site is marked with a plaque that explains the extraordinary project that was attempted there, and divers occasionally explore the underwater remains to understand what was built and what was attempted. The scientific legacy of Habakkuk extends beyond the immediate military application. The research into Pykrete and reinforced ice contributed to understanding of composite materials, particularly the properties that emerge when materials with different characteristics are combined. The refrigeration engineering developed for maintaining large frozen structures influenced subsequent work in cold storage, ice rink construction, and eventually in projects like the ice roads built in northern regions for industrial transport. The structural analysis of how loads are distributed in materials with temperature gradients informed engineering practices in environments where thermal cycling is significant. The strategic lesson from Habakkuk is less clear. Was it a reasonable response to a genuine crisis, abandoned only because that crisis was resolved through other means? Or was it a distraction, consuming resources that could have been applied more productively to conventional solutions? The answer depends partly on timing. In mid-1942, when the project began, the Battle of the Atlantic seemed unwinnable, and conventional approaches were failing. By late 1943, when the project was cancelled, the situation had transformed, and Habakkuk's capabilities were no longer needed urgently enough to justify its costs. The comparison between Habakkuk and other unconventional weapons projects of World War II reveals patterns that transcend any individual program. Projects like the German V weapons, Japanese midget submarines, British bouncing bombs, and American bat bombs all shared characteristics with Habakkuk: innovative thinking applied to military problems, engineering challenges that pushed technological boundaries, uncertain cost-benefit ratios, and outcomes that depended heavily on timing and strategic context. Some succeeded spectacularly, others failed completely. Most fell somewhere between. Habakkuk's fate was to be rendered unnecessary before completion, which is perhaps the best outcome for any weapons program. The psychological dimension of Habakkuk deserves attention. The project attracted support from serious people, Churchill, Mountbatten, Roosevelt's scientific advisors, who understood that the proposal sounded absurd, but recognized that absurdity was not necessarily a disqualification during wartime crisis. The willingness to consider ideas that conventional peacetime planning would reject immediately reflects the desperation and open-mindedness that major wars can produce. This openness generates both breakthroughs and wastes, and distinguishing between them often requires attempting both and seeing which succeed. The engineering community's response to Habakkuk ranged from enthusiasm to derision, with most engineers falling somewhere between. Those who worked directly on the project generally became believers once they understood the physics and saw the test results. Those who heard about it secondhand often dismissed it as fantasy. The division reflected differences in information access as much as differences in judgment. Engineers who could examine Pykrete samples and review structural calculations could appreciate the genuine innovation. Engineers who heard only that someone proposed building aircraft carriers from ice naturally concluded it was nonsense. Technical evaluation required technical access, and classification restrictions meant that many qualified engineers never had opportunity to provide informed assessment. The cultural impact of Habakkuk, once the story was declassified, has been persistent fascination with the idea that frozen water could become a warship. Popular accounts often present the project as evidence of British eccentricity or wartime desperation, missing the serious engineering and strategic logic that justified the attempt. Fiction writers have borrowed the concept for stories where ice carriers are successfully built and operated. Engineers continue to study Pykrete as an example of composite material design, occasionally proposing modern applications for similar reinforced ice structures in Arctic construction or offshore platforms. The memorial to Habakkuk exists in multiple forms: the declassified documents that reveal what was attempted, the photographs that show the prototype under construction, the remnants on the lake bottom that prove the project was real, the historical accounts that explain why it seemed reasonable at the time. Together, these create a record of extraordinary ambition pursued under desperate circumstances, engineering excellence applied to an unusual problem, and the essential unpredictability of war that makes even the most careful planning subject to revision when circumstances change. The men who worked on Habakkuk were not fools or fantasists, but talented engineers and scientists doing their jobs under wartime conditions. They investigated whether ice carriers were feasible, determined that they were, began construction of a prototype to prove the concept, and were in the midst of scaling up when the strategic situation changed and made their work unnecessary. This is how war research is supposed to function: investigating options, pursuing promising leads, adapting to changing circumstances. That Habakkuk was never completed is not evidence of failure, but evidence of flexibility, of recognizing when a once essential capability has become redundant and redirecting resources accordingly. The physics of Pykrete remains valid. The engineering of refrigeration remains sound. The strategic logic that motivated the project was reasonable, given the information available when decisions were made. What changed was not the science or engineering, but the operational situation that created the need. The Battle of the Atlantic was won through convoy escorts, long-range aircraft, improved radar, and code breaking, conventional solutions that worked once they were properly resourced and coordinated. Habakkuk would have provided a different path to victory, but the conventional path proved sufficient and faster to implement. 2 million tons of frozen wood pulp, 2,000 feet of flight deck, walls 40 feet thick that no torpedo could penetrate, engines producing enough thrust to push a floating iceberg across the Atlantic at 7 knots, a crew of thousands operating 100 aircraft from a vessel that could be repaired simply by freezing more ice onto damaged areas. These specifications describe Habakkuk as it was planned, a ship that was never built, but that existed in detailed engineering drawings, cost estimates, and construction schedules. Churchill approved it. Engineers designed it. A prototype demonstrated its feasibility. Only the changing war prevented its completion. Project Habbakuk was Britain's plan to build aircraft carriers from ice, approved by Churchill, pursued by talented engineers, abandoned when conventional solutions proved adequate. It was serious science applied to unconventional purposes, desperate measures contemplated during desperate times, and an example of the remarkable things that wars make people consider when survival demands innovation. The ice carriers were never built, but they were never impossible either. They were simply rendered unnecessary by the victory they were designed to enable, which is perhaps the finest compliment any weapon can receive, to become obsolete before completion because the war was won without it.